This is the first of two lectures relevant to lipid metabolism. This one is lipid oxidation, or to be more specific, beta oxidation. So once the fatty acid already arrive to the muscle cell, myocyte, it needs to be activated. Activation is to be connected to connect the free fatty acid to the coenzyme A. Therefore, it will be now known as acyl-CoA. And this reaction is done by the enzyme acyl-CoA synthetase, and that is located strategically outside of the mitochondria. The location of beta oxidation is within mitochondria. Interestingly, after it becomes acyl-CoA, in order to go from cytoplasma to inside the mitochondria, it needs to use this shuttle, the carnitine shuttle. In order to do that, it is removed from the coenzyme A and then attached to the carnitine. This carnitine is required in terms of moving the acyl or the fatty acid component from the cytoplasma to within the inside of the mitochondria. So once the acyl carnitine goes through the translocase, then once it's inside the mitochondria, the removal of carnitine takes place, and reattachment of the coenzyme A takes place again, and therefore you get the acyl-CoA already inside of the mitochondria to progress to the beta oxidation. So now we look into the beta oxidation itself, where there is 4 steps. This beta oxidation basically takes the fatty acid. The fatty acid has already been activated now. That is fatty or acyl-CoA, such as palmityl-CoA, where it can be cleaved 2 carbon at a time, where 2 carbon at a time remove as acetyl coenzyme A. And in order to each time to remove these 2 carbon, it has to undergo 4 step involving the reaction at the carbon 2 and 3. Therefore, that's why it's known as beta oxidation. And if fatty acid such as palmitate or palmityl-CoA undergoes beta oxidation in series, you will have 7 beta oxidation steps, and it will lead to 8 acetyl coenzyme A from palmitic acid. So here shown the beta oxidation, whereby there are 4 steps for each time to remove 2 carbon as acetyl coenzyme A. So you have the acyl coenzyme A, where the reaction takes place at the alpha carbon as well as beta carbon. Therefore, the name beta oxidation comes about. It starts off with oxidation of this acyl-CoA, and since it involves a dehydrogenase, it's a redox reaction where oxidation is also accompanied with reduction. So in the reduction, you will have FAD becoming FADH2. And then the next step is hydration, where the trans-enoyl CoA will undergo hydration, and it's followed immediately of another redox reaction where it will undergo oxidation as well as reduction, the formation of NADH, and the ketoacyl CoA will then ready to be cleaved, and remove 2 carbon to become acetyl coenzyme A, and the acyl CoA now has less 2 carbon, and it doesn't stop at this. It will keep on going another 4 steps and remove 2 carbon, and this goes on until all the carbon is converted to acetyl coenzyme A. So if you have palmitic CoA going through this beta oxidation, the total number of what you call cleavage is 7, while the yield is 8 acetyl coenzyme A in total. Not only that, since it undergoes 7 cleavage, or 7 of these 4 steps, therefore you should be able to have 7 FADH2 and 7 NADH. So now let's do the calculation of the total number of ATP can be obtained if palmitic acid undergoes beta oxidation followed by electron transport chain. You already know that palmitic acid will undergo 7 of the 4 steps. Therefore, there will be 8 acetyl coenzyme as well as 7 FADH2 and 7 NADH. You know also that each FADH2 undergoing electron transport chain will yield 2 ATP, while NADH will yield 3 ATPs. So if you put together the 7 FADH2 multiply by 2, you get 14, and then 7 multiplied by 3, you will get 21. So 14 plus 21, you get 35 ATPs in total for the 7 cleavage or cut that is happening on the palmitic acid. Next, we look at the fate of the acetyl coenzyme A. So now that you have 8 moles of acetyl coenzyme A, each undergoing citric acid cycle will lead to 12 ATPs. Remember, citric acid cycle will give rise to, for each acetyl coenzyme A, 3 NADH as well as 1 FADH2 and also 1 GTP, which equals to ATP. When you put together these numbers into electron transport chain, it will be 12 ATPs in total. So now you have 8 acetyl coenzyme A, which goes into the citric cycle. What you get is 8 multiplied by 12. Therefore, it is a total of 96 ATPs. So once you have these 96 ATPs, then you add with the 35 ATP, that will be 131 ATPs in total. But as you know, there need to be activation of the free fatty acid, and activation is adding coenzyme A. And in terms of palmitic acid, when you add one coenzyme A, you will lose 2 ATP. So from that 131, you minus off this 2 ATP for the activation of the palmitic acid. What you have is total of 129 ATPs net. These once been calculated is only 68% of energy that you get from the oxidation of palmitic acid. It doesn't give you 100%, and the remainder of 32% is in fact lost as heat